Okay, guys, so we are back from the regular interruption as usual. So as I was saying, we know that your pre-image is the original image or the original figure before transformation. And the image is the figure after transformation. And as I was saying, if you represent a triangle with points A, B, C as your pre-image, then the image will take A dash, B dash, C dash to represent the image, all right? So that's something to bear in mind. All right, so moving along. Now, this is what we refer to as a slide or a translation. Now, these dotted lines only give you an idea the line of displacement, right? So just imagine that these dotted lines are not there. Then what would have happened is that your image, which would be ADCB, or if you go the other way, ABCD, this would be your image, sorry, your pre-image rather. So if we go from A, B, C, D, and back to A, that would give you your pre-image. Now, if this should slide, it would slide along the dotted lines, and those dotted lines would be the line of displacement. And so it would be sliding from the left, and it would now reach the point of A dash, B dash, C dash, D dash, connecting back to A dash, all right? Now the image and its pre-image, or the pre-image and its image, are identical in size and in shape. And you notice that the orientation, it does not change the uprightness of the image. It doesn't tilt on any angle, but it remains the same angle as it was when you slide it. So in other words, we are saying that the orientation of the image remains the same. There's no turning or flipping or rotating of it. It's just a slide. So it maintains the orientation. All right. Now, even though this transformation on your computer, you would click on the image and drag it from the left side to the right side, the computer actually has to do calculation to know where you're actually putting your image. So while you're dragging it, the computer is actually calculating how far you're bringing this pre-image to in terms of a new image. All right. Now in math, we have to be able to work out that calculation in the form of a relation. Remember, we did functions and relation. So when we are working out this transformation, we have to use some kind of mathematical relation in order to get our transformation. All right, guys? And so that's what we'll be looking at shortly. All right, so that's the displacement. Now, this is how we would write the relation for this transformation. So the translation would be represented by T. And we know that if we're reading the colon in mathematics, it means such that. So you can say T such that the coordinates of X and Y will map onto. So this X and Y would be your pre-image. So this is your pre-image. So your pre-image will map on to x minus 5, y minus 4. And this now will give you your image. All right, guys, so your pre-image xy will map onto your image x minus 5 and y minus 4. Now the minus 5 and the minus 4 can be written in the form of a vector. And in the form of a vector, this vector is what we call the translation vector, right? So how does the translation vector work? Is that you would have your image, which is xy. Now in our graph, we generally use coordinates. Go ahead, Ms. Wesa.
So that vector would have been the same thing as a matrix?
Yes, it can also be thought of in the form of a matrix because vectors are also treated like matrix. They are actually matrix in their own. All right. So in that context, then, when we are dealing with these coordinates, remember your coordinates are written in the horizontal form from x coordinate to y coordinate. But when you're writing them as a vector, you have to write them in the column form. So in other words, you remember we were talking about transposing the matrix. What is row becomes a column. So your pre-image is xy, but it can be written in the form of a vector as x. Well, this one is a little bit too wide. So your pre-image can be written in a vector form or a column form as the x coordinate first, x coordinate first, and then the y coordinates. So the x coordinate above, the y coordinates below. And so this would be your coordinate for your pre-image. All right. Now, you will undergo what we call now your translation by adding your translation vector. So if you add your translation vector, you will be adding -5 and -4. And so this would be your translation vector, which represent these two numbers here. All right. And then now, once you add those, so you add just in the same way as you're doing with matrices, you are treating it like matrix, so you add corresponding elements. So the x must be added to -5, so you'll get x plus -5 would be x minus 5. And then now for the y coordinates, you would now add y plus -4. So you would have y minus 4. And then now, once you have carried out this, this would give you your result, and the result would be your image. So this will give you your image on that translation. Now, so translation vectors would be, this function would be different from the function of a different transformation. So if you're doing rotation or enlargement, you'll be doing something quite different from what you're doing here. So for translation, you're simply adding vectors in the form of matrices. All right. Now, sometimes you could have, instead of adding -5, -4, you could be adding a positive, probably a +3, a +2, whatever the numbers are that you're adding to x and y. So not necessarily going to be adding a negative at all time. It can be also positive. All right, guys? All right, so I hope that is clear for you guys. So here is what we would get. Our example here. For this example, the question is asking, what is the image of the coordinate 2, x equal 2, y equal -1 under the translation vector of 3 and 1. So your coordinates would be in the horizontal form, and so you would have to write it in the vertical form. Then you add your translation vector, and then the result will give you your image. So your image is equal to your pre-image. So this would be a pre-image plus your translation. Then you would get this as the image. All right, so if you add 3 plus 2, you will get 5. -1 plus -4, you get -5. All right, so the mapping then, your pre-image would be mapped from 2 to 5 for the x, and from -1 to -5 for the y. Go ahead, Ms. Wilson.
Sir, is it natural that we because the 2 and the -1 is in a row form, and then the translation 3 minus 1 is in a column form. So how we get if we turn both columns down here? Is it natural that we would set it that way?
All right. So because we are generally transforming points, we generally use our translation. Our translation is generally given in a column form, which is what we refer to as a vector form. In order to calculate, you convert your coordinates into a column form, because in the column form, it would be just what we would call it, converting our rows to column. So even the column form is just another form of how you can write your coordinates, right? But for graph purpose, we would write it in the column form. But when we're doing vectors, we write our coordinates as column matrix. Is that clear?
Okay, sir.
Right. So once they're given points in row form and their coordinates, you have to convert them to columns when you're actually doing the calculation. And so your translation will be also given already in as a column vector. All right, so with that, let us move on, guys. So some properties of translation now. All right, so if A and B are 2 points with images A dash, B dash, then the line from A to A dash is parallel to the line from B to B dash. And remember earlier on when we look at the slide of the shape that we presented on the slide. So let me just go back up to the previous slide. This shape, right? Now, the dotted lines would be the lines that go in from the pre-image to the image. So from A to A dash would be this dotted line. All right. So the line from A to A dash would be this line. And the line from B to B dash would be this line. And so what they are saying that the property of this, the property of translation in this slide, the displacement line will be parallel to each other. That's what they are saying. So this line will be parallel to this line. So all the displacement lines will be parallel. So even these would be parallels. So that's what it is saying. Is that clear, guys? Raise your hand if that's clear, guys. All right. So that's what they're saying now. The line A dash is parallel to the line B dash. Now, A dash, the line A to A dash is equal to the line B to B dash. What it is saying that the length of the line A to A dash is also equal to the length of the line B to B dash, right? So the third property now is that the shape and size do not change on the translation. So as you notice from what we have here, the shape of the pre-image does not change when you slide it around. So the size of it does not change and the shape of it does not change. So that's what the third point is saying. All right. Is that clear, guys? Now, when the shape and the size do not change, we call that congruencies. All right. Congruency means sameness or the same. So the shape remains the same, the size remains the same. So that's what we mean by congruency. And you may see that word, you can see it in question. So make sure you understand what it means. So it means sameness. The shape and the size of the figure does not change. All right. So with that said, then we would have gone through translation. So that would be the first transformation that we looked at. Now the next transformation that we're looking at will be reflection. Now, the definition for reflection. If a point A is not all right, I think let me see if I can figure out what happened here. So if a point A is not, all right, this is supposed to be on. All right, so if a point A is not on a point L, all right, what that means, L will be your mirror line. So if a point A is not on the line L, the reflection image of A in L is the point A dash, such that L is the perpendicular bisector of A and A dash. All right. Now that might not seem very straightforward for some of you, but what it really means is that if you have a line L, let's say that is the line L, and A, the point A is not on L, so let's say A is right here, and that is the point A. So what they are saying here, the reflection image of A is A in L is the point A dash, such that L is perpendicular bisector of A to A dash, meaning the line from A to A dash. So if this is your pre-image, which is A, then A dash would be over here. And what they are saying, the point A and the line from the point A to A dash the line L, which is this line, will be a perpendicular bisector of the line A to A dash. So remember, a perpendicular bisector means one, L is perpendicular to the line A to A dash, meaning it forms right angle to the line A to A dash. And it is a perpendicular bisector. So if it is a bisector of the line A to A dash, it means that it cuts the line A to A dash into equal parts. So in the middle here would be half of the line from A to A dash. Is that clear? So from A to L here, if that is 2, if that's a length 2, then so from the line L here to this line here, this also be 2. If we are talking about in terms of centimeters, let us attach that unit to it. Then what we are saying that the distance of your pre-image to the mirror line is the same distance of your image from the mirror line. Is that clear, guys? Raise your hand if you understand clearly what that is saying. Guys, not getting any response.
Sir, could you repeat it because you were kind of a bit breaking up.
I was, all right, sorry about that. So, all right, so as I was saying earlier, the line L is your mirror line. So the definition is saying that if you have a point A, which is not on the line L, so this point A is not on the line L, the reflection of the image of A in L is the point A dash. So if you reflect the line, if you reflect this point A, if you reflect it in the line L, the reflection would be on this side of the line, right? And so the reflection of the image of A in the line L is the point A dash, such that L is the perpendicular bisector of the line A to A dash. So this line L is a perpendicular bisector. Now, when a line is perpendicular to another line, the line is at right angle to the line. When the line is a bisector of another line, it cuts the other line into equal parts. So as I was saying, that the line from A to its image, which is A dash, that straight line, would be cut into 2 equal parts by the perpendicular line L, right? So this line L will cut the line A to A dash into 2 equal parts. So from A to the mirror line here, if that is 2 centimeters, then also from the mirror line to A dash, you'll get 2 centimeters. Is that clear now, guys? Is everybody clear on that? Did everybody get to hear me well? Ms. Green, did you hear anything at all that I've said?
You can just go over one more time, please.
All right. Did you hear me at all, Ms. Lisa?
Sir, my internet's in and out, but it's not from your side. It's just my internet at home.
All right. Can I put it in a form that you probably can relate to?
Okay, sir.
A reflection is simply if you are in the habit of drawing a heart, right? You would draw the heart such a way that you can fold the left side onto the right side.
Mm-hmm.
Everybody can relate to that?
Yes, sir.
Right. So if let's say that this is a heart, it would be you could fold it along the line L because the line would be mirror line. So if you fold over this point A, if you fold over along the mirror line, it will go exactly on this point, which is A dash. You following what I'm saying, Ms. Waysom?
Yes, sir.
And so this line L, which is the mirror line, the distance of A to the line, which is the mirror line, if it is 2 centimeters, the distance of the line from A dash, which is the image, to the mirror line must be the same 2 centimeters.
Okay.
So that's all we are saying. And,
Okay.
and this mirror line is perpendicular, meaning it is at right angle to that line from A to A dash.
Yes, sir.
And it would just cut it in 2 equal parts. That's all it is saying. All right, everybody's good with that now? All right,
Yes, sir.
that everybody gets it. All right, so note briefly, A dash is the image of A, as well as A is the image of A dash. So you can treat the image as the pre-image if you want. So if you start off with A dash as your pre-image, then the image would be A. If you start off with A as the pre-image, then the image would be A dash. All right, so vice versa. All right, so the line L is called the line of reflection or the mirror line. So every reflection will have a mirror line, guys. All right, so this is some examples of reflection with mirror lines. So the mirror line would be, for this figure on the left, the mirror line would be the dotted line coming straight down, and this would be the reflection. Now, one of the things that you should notice about when images are reflected is that you have what we call a lateral inverted image. Now, the word lateral means sideways. And if it is laterally inverted, meaning it is sideways inverted, what you notice about the E on the left and the E on the right, what you notice about them?
They are facing each other, sir.
Right, so they are inverted sideways. So in other words, the E that is pointing with the sides pointing to the mirror line, the image of the side pointing the opposite direction. So once you have a reflection, that's generally how the images will form. You will have this invertedness. Now, if you look at the right reflection, so you have the triangle ABCD. What you notice is that the point C, which is the point closest to the mirror line, the image also have C dash closest to the mirror line. And so you can notice that each of these letters have equal distance from the mirror line, and they are same length. And this dotted line that is passed through from A to A dash, that is called your displacement line. All right, or the line through which A and A dash are connected. Sorry. So what is also clear is that if you consider that to be a drawing, like a heart, and you fold it along the mirror line, then your image must match over and fit perfectly on its pre-image. Is that clear, guys? Is it clear if you fold the images along the mirror line, you will find that this triangle will fold and fit right on this one over here.
Yes, sir.
All right, sometimes in exam, students cheat when they're asked to do the pre-image. But no, sorry, when they're asked to do a reflection and they're asked to do the image, one of the things that some students will do is they will draw the points of the pre-image on the graph paper, and then they will fold it along the mirror line and then now use the point of the pencil to find where the pre-image, where the image is. You understand what I'm saying?
Yes, sir.
Right. So it's a cheat, it's a way of cheating in terms of finding the points quickly. All right. All right. So that is what you'll have to understand about reflection. So if a point A is not on a line L, the reflection image of A in line L is the point A dash, such that L is perpendicular bisector to A, to the line A dash. All right, these are some properties now for reflection. So reflection preserves collinearity. The image of a straight line on the reflection is a straight line. So what it means, if we go back to what we have here, collinearity means that if you just have a line on the left side here, if you have a line here, then reflection will preserve the same line on the other side, right? So the length of the line is the same. The only difference is that the line would be inverted sideways, all right? So that's what it means by collinearity. So reflection preserves collinearity. The image of a line, of a straight line on the reflection is a straight line. Reflection preserves betweenness. A line and its image are the same distance, are the same length on the reflection. So what we mean by preserve betweenness, we are simply just referring to the distance from the image, or sorry, the distance from the mirror line to the image will be the same distance for the pre-image from the mirror line. So it preserves betweenness. So wherever on the pre-image you are. So if you go from here to here to the mirror line, then this line from the mirror line to here will be the same length. If you go from here to here to the mirror line, this line from here to here will be the same length. So it preserves the same betweenness from the mirror line to the image. All right, so reflection preserve distance. The distance from L is the same distance as that of the pre-image, right? So in the same context, the length of the line from the pre-image to L is the same as the length of the line from L to the pre-image. Now here we have reflection preserve angle. So what it means, whatever the size of the angle is at C, so if C is 30 degrees, your image will have an angle of 30 degrees as well. So if this is an angle X, then this angle also going to be X. So reflection preserve angles. All right, so reflection reverses orientation. So when we say that it is laterally inverted, so in other words, if your line is orientated pointing to the left, when it is reflected, it orientated pointing to the right. So if you notice that from this triangle, if you're thinking of the line from C to A, from C pointing to A, when it is reflected, so this one pointing to what you would consider the west, and this one would point to the east. Right, so that's what this is saying. So we are saying that reflection reverses orientation. Now, figure is oriented in one direction and its corresponding image oriented in the opposite direction. All right, so this is a summary of the properties of reflection. So every point has exactly one reflection point, known as the image, and reflection preserves collinearity, betweenness, distance, angles of measure. All right, so these are just summary of what we just look at. All right, so our next object we are going to be looking at now, a figure is known as what we call reflection symmetric. So what do we mean when we say it is reflection symmetric? Now, remember when we were looking at graph and we talk about the line of symmetry, right? And we say that when you fold the graph through the line of symmetry, the left side must map onto the right side. So when we say reflection symmetric, this shape would be reflection symmetric about the line from A to C. Because once you fold it along that line, the left side will be mapped on to the right side. So this is the idea that we are referring to. All right. So we say a figure is reflection symmetric over a line L if and only if it is coincided with its reflected image in the line L. Now, the line is called a line of symmetry of the figure. So in this figure, the line of symmetry would be the line from A to C, because when you fold it, the left side will coincide with the right side. Everybody see that? Now, could you have folded this along the line BD and have it to be reflection symmetric? Guys?
Sorry, repeat.
If you fold line, if you fold this image